So that was a very straightforward problem. The equation was given to you. So let's take a look at one that takes a little bit more work in setting it up. So we'll look at this problem in which we're told that a ladder is leaning up against the side of a building. The bottom of the ladder slides away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving when the bottom is 5 feet from the wall? Okay, so let's first, again, let's circle all of our numbers and variables if they're there. We've got a 13-foot ladder. So we've got a 13-foot ladder leaning against the building. If the bottom ladder slides away, so here's a rate, 2 feet per second. How fast is when it's 5 feet from the wall? Okay, so we've circled our numbers, and now we're going to underline our question. How fast is the top of the ladder moving when the bottom of the ladder is 5 feet from the wall? So there is our question. And now we're going to box any of our math actions. So leaning, if the bottom of the ladder slides away at a rate, so that is a math term, right? Rates should immediately trigger in your mind the idea of a derivative. So the bottom of the ladder is sliding away at a rate. How fast? That is just another form of rate. Speed, right? How fast is the top of the ladder moving when the bottom is 5 feet from the wall? And even this right here, from the wall, is a mathematical statement because that's distance, right? And we'll need to work that in. So those are we've circled, underlined, and boxed, and now we need to eliminate if there's anything extra. And again, I don't see any extraneous variables in this problem. Okay, so now let's organize our work. So I've got a 13-foot ladder leaning against the side of a building. So the first thing I'm going to do is draw a picture. So I've got a building, say here, some building, and I've got a ladder that's leaning against it. And let's give some ground here. So this is the ground. It's supposed to be flat. We'll take that as a consideration. So there's our ladder. And it's a 13-foot tall ladder. So this distance here of the ladder, so I can put it right on my diagram, is 13 feet. If the bottom of the ladder slides away, we know that something is changing at a rate of 2 feet per second. And so we're going to have to decide to introduce some variables here. So let's go ahead and since we want to talk about the distance of the ladder from the base of the wall, that's going to be something that varies. And I'll, just for simplicity, call this x. And we want to know the rate at which the top of the ladder is changing. So that's this distance here. And so this distance, the distance of the top of the ladder to the bottom, I'll call y. So both these are going to vary, right? Because as it slides down, the bottom of the ladder is moving in some direction, right? And the top of the ladder is going to change. So these are both variables. I know that from reading the problem. I've got rates of change. I've got things moving along. And I'm told that if the bottom of the ladder slides away from the wall at a rate of 2 feet per second. So now I know the bottom of the ladder is, maybe I should write out what x is. X is distance of bottom of ladder ladder from wall. And y is same thing, distance of top of ladder from ground. Right? So x is the distance. So this is really good practice to write out exactly what your variables are, because oftentimes you get in the middle of a problem and you forget what your various variables are, and then you get lost in how to solve the problem. So highly recommend writing it down. And so now, since I know that the bottom of the ladder slides away from the wall at a rate of 2 feet per second, that tells me that dx dt is constantly 2. And I'll put my units 2 feet per second. And again, how do I know dt? Because the information is here that the rate of change is with respect to time and not distance. So it's not going to be dx dy because y is a function of distance. So dx dt is 2 feet per second. And the question being asked is how fast is the top of the ladder moving? So what is dy dt? So this is our question. When the bottom, so what variable is that? That's x. When x is equal to 5. Okay. Now, this is pretty much what we did in the last problem, except for if you recall, we had an equation that we differentiated. If we look at the gathered information here, there is no equation yet. I've got no relationship between x and y. But the picture should be extremely suggestive of a relationship between x and y because I've got a right triangle here. And we're going to assume that the building is upright. And so I've got a right triangle. And so I know from Pythagorean's theorem that x squared plus y squared has to be 13 squared. So here's my relationship. And now from this, I'm going to get to be able to use implicit differentiation. So now I've related everything. I've organized all my thoughts and idea, and now I've related my variables. So this is the R step. I've got x squared plus y squared is 13. And now I need to determine my approach, and I'm going to use implicit differentiation. That's my approach. Again, why do I choose that? Well, one, I'm telling you that implicit differentiation is the main tool to solve related rate problems. So I've got that x squared plus y squared equals 13. So using implicit differentiation, I know that the differential of x squared plus y squared has to equal the differential of 13 squared. And notice I'm not even squaring out 13 squared because I know the differential of any constant is 0. So this tells me, and pushing the differential through, this distributes across addition. I've got the power rule, so I'm going to not be as detailed as I have been maybe in previous videos. I'm going to skip the differentiation part. I'm hoping that you have become a master at differentiating, and you know that the differential of x squared is 2x dx, the differential of y squared is 2y dy, and the differential of a constant is 0. Now again, in implicit differentiation, you would divide by dx or dy depending on which one you're looking for. But now I want to know dy dt. And so I don't want to divide by dx. I want to divide by dt. So I divide this entire equation on the left-hand side by dt. And of course, that means I divide 0 by dt, but that's just 0. And so I get the relationship that 2x dx dt plus 2y dy dt is 0. And what do I want to know? I want to know dy dt, and I haven't used this bit yet, so I'm going to throw this in, that dx dt is 2. So this tells me that 2 times 2, so 4x plus 2y dy dt is 0. And then solving for dy dt will be equal to negative 2x divided by y. So there's dy dt. I've got an equation for it. So I'm going back to my problem. I want to solve what is dy dt when x equals 5. And I am a little bit disturbed because my relationship has x's and y's. However, recall that we have a relationship between x and y, that x squared and plus y squared is equal to 13 squared. So a little bit of side work over here. If x is 5, I'm going to have 5 squared plus y squared is equal to 13 squared, or that y will be plus or minus the square root of 13 squared minus 5 squared, which is equal to 12. Of course, it's plus or minus purely from an algebraic or number sense, but in our problem, y can only be positive. The ladder can't fall through the ground and start having negative heights from the ground, so we'll only take the positive one. So using that information, finally solving the problem, we get when dy dt, when the point, we're going to look at the point xy is equal to 512, and that's equal to negative 2 times 5 divided by 12, which is negative 10/12, or simplifies into negative 5 over 6. And what are our units? Feet per second. So we determined we were going to use implicit differentiation, and we've solved it. And let's make sure that our solution makes sense. We found that the rate at which y is changing is negative 6 feet per second. So the negative means that it should be decreasing. Well, let's look at the picture, and that makes sense because the height from the ground, it's decreasing. We know as the ladder slides out, the top will slide down, and so it should be a negative rate of change. And so finally, our answer to this question of how fast is the top of the ladder moving when the bottom is 5 feet from the wall, we would answer it saying that the top of the ladder is descending at a rate of 5/6 feet per second. And notice I didn't use the negative. Let me repeat that. It is descending. So that is incorporating the negative sign already. So it's descending at a rate of 5/6 feet per second. If you wanted to keep the negative sign, then you would say that the top of the ladder, the position of the top of the ladder is changing at a rate of -5.6 feet per second. Subtle differences there, but again, I want to stress that.